Okay, off we go. So here's what we were talking about last time. Just a super quick review. We had this construction called a scalar surface integral, and we kind of went towards trying to apply that idea to addressing flux. And in particular, while we had previously in Chapter 3 talked about flux through a flat surface with a constant vector field, how do you deal with that if the surface is curved, right? And so you have a situation like this. And of course, what we decided to do, again, with scalar surface integrals in mind, was let's chop that surface up into little bitty pieces. On each little piece, the idea is that the question should be relatively easy on that little piece. I mean, after all, the little piece is approximately flat, sufficiently small that the vector field is approximately constant, right? And so on each little piece, the problem is easy. And after all, that's kind of how integrals go down, right? Is that, you take a hard problem, you chop your domain up into little pieces on which the problem is easy, and then you add them up. So every integral we've ever seen follows that pattern, and so same strategy here. The thing is that if you look at what you end up getting and sort of the best way to rewrite it, the thing we have to notice is that the differential is now a vector, and the integrand is now a vector. So this is a new construction, what we're going to call a vector surface integral. So just again as a reminder, when we were looking at line integrals, we tried to apply the idea of line integrals to computing work and found ourselves with a new kind of line integral called a vector line integral. Morally equivalent thing here. We had a surface integral we applied to a specific physics application, in this case flux, and again we get a new kind of surface integral, a vector surface integral. Okay, let's see here, and then there was, there's the computational details. This construction that we wrote down on the previous page, making use of all of this groundwork that we laid last time and the time before, I guess it was, allows you to rewrite and get a computationally convenient formula for computing flux. And I think the last thing we did last time was to actually apply that formula, namely, wanting to compute a flux, using this formula, all of which is based on a parameterization. Remember, the capital N is computed from a parameterization. We do pullbacks of x, y, and z by way of the parameterization. Okay? And so all of this is computable through the parameterization. Okay. All right, so picking up from there, don't forget, I put this asterisk right here. Right, we have I claim a little math crime that has been committed. Right, I argued seemingly reasonably that, well, look, this capital N vector has a direction and a magnitude, unit vector direction. Okay, well, little n, right? Isn't that the unit vector pointing in that direction? The magnitude, of course, is this right here. So shouldn't this work? And I claim that it doesn't actually quite work. So what's going on there? What's the problem? So the problem is about orientations. Oh, and I should hit that button. There we go. Okay, we can see a little bit better there. So the problem is about orientations. And you got to keep in mind that the surface originally comes to us, this surface that we're looking at, it comes with an orientation. This is not just a dumb surface, this is an oriented surface specifically. So now it could have come oriented upward, it could have come oriented downward, I don't know. Whichever those is selected, of course, though, indicates what the orientation is on our given surface. And this vector indicating the orientation, whether it's the up or the down, right, that vector is going to be called our orientation unit normal vector. Okay. And with that given, we then parameterize the surface while completely ignoring that orientation. We tend to, when we parameterize surfaces, we just kind of write them down, right? Look back at all the discussion that we did last time or the time before when we were talking about parametric surfaces. We didn't give any discussion at all to the orientation that we were creating when we did that, right? So, in particular, though, what we see now is when you parameterize the surface, that gives you your various partials. That gives you, by cross product, the capital N. And that gives you, by normalizing, this other, what we call the parametrized unit normal. That is a consequence of our parameterization. So, we kind of swept all this under the rug, again, on purpose, for dramatic purposes, right? So that we could have this big reveal here. But we had previously swept all this under the rug, but there are two unit normal vectors that we have to pay careful attention to. One that is an obligation to us, right? One that comes with the statement of the question and that we're responsible for respecting. And the other that we make up unwittingly, randomly, kind of, you might say. Right? So I can't just go around claiming these are the same. They might be. It's a coin flip, right? 50-50, maybe I got lucky, and the unit normal that I inadvertently created might be the unit normal that I'm obligated to pick. But it's, like I say, a coin flip, and so I just as likely might not have. So anyway, that's the little crime that I committed down here. And reproducing the relevant equations from the previous page, this right here, that's the orientation unit normal. This comes from whatever it is that we're given about the surface right here. Right? This is beyond my control. This is something that I have to follow. I don't get to make this. Right? And then I made my parameterization, and therefore the blah, blah, blah. I made a bunch of stuff that all comes out of the parameterization, one of which is the parameterization unit normal, which governs which direction my capital N vector points. So when I claimed that these two things were equal, effectively I was claiming that the orientation unit normal and that the parameterized unit normal are the same. And I had no basis for making such a claim. Right? I was sweeping this coin flip potential for being wrong. I was sweeping that entirely under the rug. Everybody see what the problem is? Okay. So it's a nasty little issue. Bad news, good news. The bad news is it's really hard to tell as you are parameterizing a surface. It's really hard to tell which way you're parameterizing, whether you're parameterizing right side up or upside down. It's just, we don't have, it's something we can compute, but it's not something that's easy to just kind of intuitively tell, such as when you're parameterizing curves. Now, if you think back to how you parameterize curves, your parameter, you think of it as being time. As you write it down, you can almost see which way you're going, right? We don't have that point of view with surfaces, so we just really can't tell. That's the bad news. Here's the good news. The good news is you don't really have to worry about it much as you're parameterizing. You can just look after the fact, just look and see if you might have parameterized it upside down, and if you did, no sweat. You're off by a minus sign. Toss in an extra minus sign, and you're all good, right? So you do have to worry about it. You just don't have to get it right from the very beginning. Okay. So now the way I like to write this in the formulas, it's tempting to say that the ds vector is capital N du dv. This is something that you would naturally write down if you were sort of oblivious to this point that we just realized. But again, this might be wrong. The ds points in the direction of the orientation. The ds is intrinsic to the surface. Capital N is not. Capital N comes from the parameterization. So there is the potential conflict in there, and I recognize that by putting this question mark there in recognition that, I don't know, these may be backwards of each other. Okay, so let's see this in action. How are you actually in practice, day in and day out? How are you going to deal with this? And you'll recognize this example is the same example that we did last time, right? What we ended with last time. Same vector field, same paraboloid, same portion above the same unit square, with one difference. This time, it's oriented downward. So let's think about how we're going to address that. Okay, again, as I said before, you start by ignoring it. Don't worry about it. Just for the just to get started, pick your favorite parameterization. I like the graph parameterization. This is the same parameterization we used last time. Go ahead and take those derivatives. Partial derivatives, right? Go ahead and take the cross product to get your capital N vector. All the while, not even worrying about whether you parameterize right side up or upside down. But at this point, you have to pause. And this is really important. Again, this is don't make the mistake of falling for the idea that, wow, it's just a minus sign, and minus signs, come on, what's the big deal, right? No, this is an important concept of the course. This is a challenging and sophisticated idea of the course. This matters. This is an important minus sign. This is something you have to get right to have a good solution. So at this point, we stop. And we sort of reevaluate where we are, and we see that the surface came to us, our surface came to us oriented downward. We have inadvertently parameterized, I'm going to say, kind of upward. And tragically, these are not consistent. Now, full recognition, by the way, real quick. This capital N vector does not point exactly perfectly straight up, right? But there is no reasonable sense in which you would call this vector downward, right? So we'll talk later about the language and the sloppiness, intrinsic sloppiness in the language, and why that's okay in a couple of minutes. But clearly I got it wrong. Okay. So what we're going to do to fix it is recognize we got it wrong. Right now, I wrote no here because I had written out this, this verbose phrasing of the question addressing the matter here, and I could just say no. You might just say on your exam, you might write backwards, exclamation point, frowny face, something like that. Right? Terse is fine, but you need to recognize that you have a problem, and then you just fix it by tossing in a minus sign. And now you're good to go. Proceed with the calculation. Everything's fine. That make sense to everybody? Okay. You don't have to go back and reparameterize, right? And that would be the big fear that, I parameterized it wrong. I guess I have to parameterize it right and then do all those calculations again. You don't have to. Go ahead and parameterize it wrong. And then just fix it after the fact. Okay, now there is another subtlety that we have to worry about here. I think this is important. Y'all have heard me say this a million times. You'll hear me say it several thousand more times, I'm sure. It's not about the answer at the bottom of the page. It's about the reasoning that leads you to that answer at the bottom of the page. Right? So when I say stick in a minus sign, it's very important that you stick it in the right place. It really makes a difference to the reasoning. So again, let me show you what I'm talking about here. The flux that we've been asked to compute. When I write this is a direct reference to what I've been asked. This, therefore, is a reference to what's given in the statement of the question. This is in reference to the flux oriented as asked. This notation right here, you notice the ds vector. The ds vector is pointing in the direction of the given orientation, unit normal. So this too, these are consistent with each other. These are always the same. However, this integral right here, this one you can see right there. This one is the one that is not consistent. This points in the direction of the parameterized unit normal vector. So this is where it happens, right? This is where the question, references to what was asked in the question change to references to how I specifically parameterized it, and in this case, upside down. So this is where the minus sign goes, specifically right there. Now, just to be blunt about the whole thing, let's think about what would happen if you got the minus sign in the wrong place. Of course, now this integral here that follows also comes straight out of the parameterization. Let's suppose that instead of putting the minus sign here and here, let's just say, what if I put the minus sign only there? And let's just think about what is written on the page, and is what is written on the page true? Right? It's a big deal, right? Did I write true statements? And tragically, I have a problem here, because without this minus sign there, right, this equation says that these two integrals are negatives of each other. They are not. These two purple integrals are equal. I'm saying they're negative as I have it written here. They are actually not, I'm saying they're not equal. They actually are equal. That's wrong. And likewise, super annoying, having forgotten that minus sign, this statement here also wrong at this point. Without that minus sign right there, I'm saying that this blue integral is equal to this purple integral. And again, with the orientation in mind, no, the whole point is that these are negatives of each other. So, look, persnickety, picky, okay, sure, right? But this is important to communicating your understanding of what's going on here. Again, yes, I'm perfectly well aware that if you leave off this minus sign and start with your minus signs here, yes, you will get numerically the right answer at the bottom of the page. And again, that's not what we're interested in this course. We're interested in valid reasoning and demonstrated understanding of all the relevant tools and ideas and, objects, etc. Okay, so think it through carefully. Make sure you get the minus sign, but also make sure you get the minus sign in all the right places. Let me pause there for a moment. There's a lot to think about there. Any questions? Everybody all right? Okay, so let's talk about the language. This is a little awkward. Let's think about this surface right here, just to get the ball rolling. That paraboloid. There are two different ways that surface can be oriented. We indicate orientations by way of these unit normal vectors. And so one orientation would be indicated by all of these choices that I have in green. The other orientation would be indicated by these normal vectors as I have indicated in blue. And now, how would I precisely and perfectly represent, let's say, this green orientation? What would I say about those normal vectors? Well, I mean, if I wanted to literally describe them exactly, precisely, I'd need to write down equations. And that's a pain, and not really what I need to do immediately. In the statement of the question, I really just need to distinguish between these two options. So I don't want to write down something that's precise and exact. What I really need is something that is unambiguous. That's all we need. I need an unambiguous distinction between these two possibilities. And I claim that this language right here, calling these two orientations upward versus downward, I claim that this is perfectly good enough for those purposes, right? If I say upward, there's no way I could be talking about these blue vectors, all of which point at least somewhat downward and not even a little bit upward. Right? And then likewise, if I were to say downward, well, there's no way I could be talking about this green orientation, because none of these vectors point in any sense downward. They're all at least somewhat upward. So this language right here, we choose this language to distinguish between these options, not because they're exact, they aren't, but because it makes an unambiguous distinction between the two possibilities. How are we doing? Everybody all right? All right. Okay, now another option that you could do, I'm less happy about this second option. You'll see here is, kind of okay, I suppose. To say inward versus outward, my beef with this is that, well, technically there is no inside. This is not a closed surface. There is no inside. The what you might want to call the inside is infinite and unbounded, just like what you might want to call the outside, also unbounded. So I think it remains that most people, if you were to say inward, they catch your drift, right? They know what you're talking about. But nevertheless, it leaves a little something to be desired. Okay. All right. Now, tragically, you can't just stick with this in all cases. Let's think about this surface right there. And again, we have two options for orientations. We have that one in, again, I'll use green. And then there's also this one that I'll use blue. And how would I distinguish between those? Well, if you were to if you were to try to distinguish between those by saying, for example, upward. Some of these green vectors are upward. Some of these blue vectors are upward. That doesn't remove the confusion, right? You say upward, I don't know which one of these you mean. Does that make sense to everybody? You say, wait, this is just not acceptable. These words do not remove the ambiguity, but these words here do. Fine and dandy, right? The green one is inward, actually inward. All of those vectors, right? There is a well-defined inside on this surface, right, and a well-defined outside, so that's okay. All right, so you can look at the other examples that I have on here. Try to make sure to always think about the surface in question whose orientation you're discussing. Think about what the two options are. And make sure to choose your language on the basis of what will unambiguously distinguish between those two possible orientations. Okay, how are we doing? Is everybody all right with that? Okay. Related stuff. Several related topics we need to talk about. Lucky coincidences. We saw some of this with vector line integrals. Sometimes, the nature of the problem just makes it a lot easier. You don't have to actually parameterize and, plug it all in and such. So, for example, notice here our sphere, rho equals 3, centered at the origin. And that means that the position vector and the unit normal vector are parallel. Knowing that they are parallel, you can just write down, very conveniently, just, simple geometric argument. You can write down exactly what your unit normal vector is. Notice I didn't write this down on the basis of a parameterization and the partials and the cross product and the normal, I didn't do the usual song and dance to get to this. I just write it down from geometry. That's a tremendous savings of effort, right? And by the way, this little wonderful convenience, we've seen this before, right? On an example some time ago, I don't remember exactly when. This is a peculiarity of spheres. Is that cool? Is everybody all right? Do y'all have any questions that I can help you with? No? Okay. All right. So this is a peculiarity of spheres, right? So when you find yourself looking at a sphere, try to take advantage of that if you can, and this is one of the nice ways that you can do that. Now, in this case, it actually helps the computation. You look at what we have here. This is the formula for the normal vector that we just wrote down. Our vector field, of course, we're given, and super conveniently, you can crank out this dot product, and it's just 0, and thus the whole integral is 0, and we walk away, never having to exert any real effort. Does that make sense to everybody? All right. Okay. All right. Now here's another example of geometric good fortune that can come your way sometimes. The surface that we're talking about here has a little bit of a scary description. You notice that there's a quartic inequality there. That's a little intimidating to look at. I'm not happy about that. But, very importantly, it's sitting inside of that plane. And complex though that inequality may look, that plane is really easy. That plane is just that right there. So my surface, it has a weird edge to it, but the surface itself is actually pretty, it's just flat with y equals 3. So couple of really nice things come out of this. For one thing, keeping in mind that we're interested in flux. Flux is an integral that happens on the surface. And since the surface is entirely within this plane where y is always 3, that means that I can just plug that in, right? I literally have y equals 3. I can plug that right into the vector field, and notice in particular my second coordinate there. Because y is 3, that second coordinate will always just be 0. So I get to plug in for that. And all of this ugliness of this second coordinate of my vector field, as far as I'm concerned, because we're on this surface, it's just 0. That makes sense to everybody? I emphasize, that second coordinate, it's not 0 over here. It's not 0 way over there. But I'm never going to be over here. I'm only interested in computing an integral on this surface, and on that surface it is flat 0. So heads up for that sort of thing. That's really nice when that happens. The other advantage that we get, and all we need to know is that this is inside of that plane. Notice that means that our normal vector is easy to write down. Right? We have this plane, y is 3. That's the direction perpendicular to that plane. So that I can just write down. No parameterization required. So what would in general be a, parameterize and deal with a lot of ugliness example, now we're looking at an integral where the integrand is, again, just obviously 0, and therefore the integral is 0. So again, big capitalizing on the geometry of this problem. Everybody see how that works? Questions? Feel free. All right. Okay. Now, y'all probably remember when we were talking about vector line integrals, I pointed out there was an alternative notation for vector line integrals. We talked about this coordinate line integrals business. And it was this bulky notation that doesn't seem to offer any advantages to us, right? But it does offer advantages in other contexts, and as such, other people like to use it, and as such, you're going to see it, right? So coordinate line integrals are in your future, and you have to know how to deal with them, and that's why we had to talk about that. Well, I'm sorry to say, there's also coordinate surface integrals, and these too are in your future. And it's not going to be helpful to you, particularly, but you're going to have to know how to deal with it. So again, it comes out of just taking formulas that we already know. Here's our old formula for the ds vector, into which I plug our old formula for the capital N vector. And what do I get when I just write these out in coordinates? Just write down what the coordinates are. And having written it down in coordinates, you can do this cross product. The cross product will end up being that. You may recall I waved my hands at this last time before, sometime recently. And we mystified over why would two-dimensional change of variable stretching factors come up when we're talking about surface integrals in space, right? And I so wish we had time to talk about that. It's a really interesting little point as to why these arise and why is this actually pretty natural geometrically. And if you're interested, come talk to me in office hours. I'd be very happy to show you. We just don't have time to go into that. So I'm just going to leave this as a mystery. But what you can do with that, as we have further down here, you can distribute the ds dt, and then you can look at these coordinates one at a time and recall that, I mean, we've already kind of, right, we've seen this kind of thing before. The whole reason we like this notation for the Jacobian determinants is because it makes it look like there's a cancellation, and then we rewrite this as dy dz. Look great on the page. And then likewise for the others. So we would be comparably motivated to rewrite that as dz dx and to rewrite this as dx dy. So with that done, so ds being rewritten as that, and keeping in mind that our vector field has coordinates like that, you can see where this is going to go, and you crank out this dot product, and you get this right here. So there's our alternative notation. If you have a flux, your alternative notation is to write it like that. So why would you ever want to do such a thing, right? I mean, you give me my choice, nice, compact, geometrically natural things like the vector field. That's the flow or the force or what, something natural in the statement of the question. The ds vector is telling me about little pieces of surface. I like that, geometrically meaningful and communicative. What are these things? It's not at all clear at a glance what these things are talking about. And of course it's huge and plunky and bulky. So again, there are two reasons why you need to know this. One is a cultural point, and this is a math course, and I know that a lot of people think that math's about computation, and there's a very strong component there. But hey, math is a Trinity College of Arts and Sciences, right? This is a pursuit of truth as well, right? And along those lines, it's a good cultural thing to know that this is what differential two forms look like, very largely. And that's powerful stuff. There's really, really important things that you can prove using differential forms which look a lot like this. So there are really great reasons to like this notation. They just aren't going to come up for us. But because there are good reasons to like that notation, some people you will work with or for will like this notation. So you're going to see this notation. So heads up, that's what that is. And my advice is that when you see something like this, what you should think is, all right, well, look, all this business with the dy, dz, dz, dx, dx, dy, that's just a fancy way of saying ds. And as such, then, accordingly, lined up accordingly, these scalar integrands that you see attached to those coordinate differentials, that's just a fancy way of telling you what your vector field is. Okay. All right. So there's that. How we doing? Any questions? Okay. All right. Okay, symmetry. Y'all have seen this before a bunch of times. Here we are again. You'll notice the way this theorem lays out on the page, shockingly familiar, right? Very, very similar to what we've written down before. Notice, shockingly similar to nota benes to keep in mind as well. Just like every other symmetry theorem, odd symmetry theorem that we've seen before. So all good, and I hope you will use this theorem. Scalar surface integrals are 0 when the integrand is odd and when the domain is symmetric. Both conditions, same plane, right? Same little disclaimers. All good. The bad news, the thing to be on the lookout for, the danger here is that this applies only to scalar surface integrals. Just scalar surface integrals. Quick reminder, we made a very, very similar observation about scalar line integrals. And again, it was only scalar line integrals, not vector line integrals. So likewise here, only scalar surface integrals, not vector surface integrals. And if you try to make a odd symmetry argument with vector surface integrals, well, your vector surface integrals, part of the deal is that normal vector, and symmetric though that surface is, these normal vectors, they're not equal to each other. Right? The little areas, maybe, yeah, sure, right, fine. Right, but the normal vectors, they're not equal. They're not negatives. There's nothing you can do with that to recover an odd symmetry theorem. So it just doesn't work. Now, just for the sake of completeness, I will point out there is a different kind of a symmetry theorem that does work, and it's very much not worth the trouble in my experience. There's a lot of subtleties. There's a lot of ways to accidentally get it, so close but wrong. And it's really not worth the trouble. So I'm just going to say for vector surface integrals, you just can't do it. All right. Questions? Okay. All righty. Okay, last thing I'm going to leave you with is I claim that there are some really strong analogies between vector line integrals and vector surface integrals. I believe it's fair to say that this should be surprising. After all, vector line integrals developed out of computing work involving forces over a line, over a curve, right? Whereas vector surface integrals come from thinking about fluids and surfaces. And it is a totally different geometry, a totally different physics that motivated these two constructions. And yet, there are some shockingly strong analogies between them. And in fact, we've kind of been seeing some of that as we've been going through here. I don't know if you noticed, but this page about the symmetry theorems, I deliberately laid it out on the page to be really, really analogous to the, same thing for line integrals. And the coordinate version of these, again, laid out on the page, if you compare and contrast, pretty similar to for line integrals. And the geometric coincidences, issues with orientation, there's some differences, of course, but there's a strong analogy as well. So we've already seen a lot that they have in common, and now we're going to see even more details about how much these totally different constructions with totally different motivations are really, really similar to each other. Ultimately, the reason why is because both of these constructions are integrals of differential forms. And again, can't tell you what that means in this course. But again, you don't have to know exactly what that means to be able to capitalize on the fact that they are special cases of the same thing. They are very closely related, and that's why we're going to see all these analogies that we're about to see. So here we go. Start with this like this. Here is a admittedly weird-looking picture of a parameterization of a curve. I had to do kind of an above and below kind of angled thing because I just didn't have the width on the page, right? So sorry about that. But parameter space goes into the parameterization. Out comes your parametric curve, and then likewise, here is a again, weirdly drawn, but parameterization of a surface. We have a parameter space, 2 parameters, of course, and then the resulting parametric surface. And now let's talk about them. From each of these parameterizations, we can take various derivatives. When you take a derivative of a parametric curve, you get the velocity. When you take partial derivatives, but then you do the little cross product. Something that comes out of taking derivatives of our surface parameterization gives us our capital N. So both of these, loosely speaking, if you will, I'm going to say are kinds of derivatives of our parameterizations. And notice, unexpectedly, where they lay out on the page in these equations. All these equations down here are old news. We've seen all these before. This is just kind of a summary comparison page. They lay out in exactly the same places. Likewise, the unit vectors. The unit tangent vector and the unit normal vector. Pointing in the same directions as the derivatives. Both of which give us our orientations, right? This one by telling you the direction along the curve. This one by giving you the chosen direction through the surface. Geometrically different, but both telling us our orientations. They lay out on the page in the equations analogously as well. Okay, let's talk about sizes, right? We've got ds representing how long a piece of curve is there. We've got d capital S representing the area of a piece of surface over there. They lay out on the page analogously. It's real surprising. What are the odds, right? Totally different scenarios. Why does a work calculation and a fluid flux calculation, why do they have so much in common? It's just really kind of very, very unexpected, right? And the analogies continue. If you look at the dx vector and you look at the ds vector, keep in mind both of these vectors, dx and ds, they point in the direction of the orientation. Their magnitudes are these sizes, and they participate in the equations in totally analogous ways as well. So that is super duper weird. And the analogy continues if you, get this, there we go. If you look at how these things lay out on the page in these various different equations, again, nothing particularly new here. All this is stuff we've talked about before. Pretty much. You continue the color coding down here and the pattern continues. Right? So the color symmetry that we have there, likewise color symmetry down here. So what's this good for? Well, Again, I can't tell you differential forms. I can't tell you integrals of differential forms. But what we're seeing here are consequences. These are what I'm going to call the shadows, right? The Math219 level shadows of these much more sophisticated objects. And I think it's just, it's really interesting. These are clues that there are deeper ideas afoot, right? Even if we can't see them. And again, for cultural reasons, I think that's really good. The other thing is useful to y'all in terms of understanding, and that is, I think analogies are really, really helpful. I'm a big believer, right? So for example, let's suppose you feel really good about all this stuff with the vector line integrals, but you're kind of not sure what's going on with the vector surface integrals. The fact that this analogy is so strong allows you to take whatever it is that you understand over here, and that gives you suggestions of ways you should think about the stuff over here. Right, so how should I think about capital N, for example? A lot of students are like creeped out by capital N. It's this formula. I don't know why I care about this formula. Well, capital N comes from derivatives of the parameterization, just like V comes from derivatives of the parameterization. Capital N is the thing whose magnitude is the stretching factor, just like V, by analogy, is the thing whose magnitude is your stretching factor. And so, understanding what's going on over here, you can kind of map that over and help you gain an understanding of what's going on over here. All right, so I hope you'll find that to be useful. And we're going to proceed along now, and I believe we're entering now into section 7.3. 7.3 is a big one. We'll do just a little bit, very little bit of this, but I want to give you a little bit of context first. I've made fun of Colley's book a little bit for being highly inconsistent with their section content levels. Right? We had a section back in chapter 5 that was like really, really short. We spent 5 minutes talking about it. There's hardly anything to say. Right? The one about switching differentials. It's basically one example. And then we have section 5.5, which was change of variables, big topic. Coordinate system integrals, big topic. And symmetry, that also a pretty big topic. There's just it was more than a week of discussion for that section. So I think the same thing's going on at 7.3 here. This is a massive section. There's a tremendous amount to say about that. Either one of these theorems, Stokes or Gauss, take your pick, either one of them by itself, there's a lot to say. And in addition to the theorems themselves, there are some tremendously strong applications, tremendously important applications that I think really need to be talked about as well. So we're going to spend just a ton of time in this section, and I don't know exactly how many days it's going to be, but we're going to be in 7.3 for a while. Okay, real quick, just as a heads up, these two theorems, Gauss's theorem, Stokes' theorem, so much like Green's theorem. Really, really similar to Green's theorem. Really, really similar to the other similar theorems that we've talked about, like the 2D divergence theorem, the fundamental theorem of line integrals, the fundamental theorem of calculus. In all of them, we need to understand what we mean by boundary and the associated orientation. There is a relevant accumulating quantity that we need to identify and establish accumulates over the domains in question. We need to observe that means that your accumulating quantity can be treated as if it's a physical stuff, even if it isn't. Behaves like stuff, so you can treat it like stuff. There's an associated notion of density, therefore. And that when you put the pieces all together, you get a theorem. Now, you're going to notice that, again, I do all this on purpose, right? I've deliberately organized the development here. We're starting with Gauss's theorem. I've deliberately organized this to be exactly the same sort of order of, outline of these ideas as we used for Green's theorem. So again, my goal here is to underscore as much as possible how much these theorems are so analogous to each other, because I think, again, tremendous value in seeing those analogies. So as we go through all this stuff, compare and contrast. Be flipping back in your notes go back to compare to Green's theorem and notice how different, of course, but how analogous the ideas are as we develop them. Okay, so we'll draw the line right here and pick up here on Friday. Y'all have a good rest of your day. See you later. Don't forget about attendance if I didn't already get you down. Just 1 second here.